my name is Alexander Chin. I am a researcher and a student under Dr. Incorvia, and today I'll be presenting my simulations and research on stochastic ferrimagnetic tunnel junctions. So again, Nicholas did the honors of explaining everything for me for the background, but I'll touch on it briefly with the motivation. So it's essentially why true random number generation, AI. But essentially, AI, or in terms of like generative AI, you actually have to sample random numbers at every iteration. And for an example here is I'm showing a very simple diffusion model where both in every iteration of training and sampling, you have to sample from different distributions. Here's the uniform distribution and the Gaussian distribution. And the issue is right now we're using pseudo-random number generation because it's fast, it's energy efficient, or I guess Nicholas said it was, I mean, it's still CMOS, so there's a joule heating loss, but you run into this issue with pseudo-random number generation is whenever you're trying to sample like hundreds or thousands or even, so like if you keep scaling and you try to sample from the same stream, if you don't choose your seeds correctly, your bit streams could actually overlap and then you have underlying correlations between your bit streams. Here's just one additional problem with that, with scalability. Also, in the case of cybersecurity, if you choose to seed your pseudo-random numbers with like date or something, that can easily be compromised, and then the strength of your keys will just go out the window. So we turn to MTJs because we can leverage thermal effects and create a entropy source using them. And so you can actually create true random numbers, which solves the cybersecurity case. It's also tunable, which allows you to create custom distributions instead of having to sample strictly from a uniform distribution. You can actually directly sample from, let's say, a normal distribution. But the main limitation I wanted to talk about is the speed limitation, where sampling speed is limited by ferromagnetic resonance, which Shafin actually talked about briefly in his presentation. So, did I go back? Oh, no. So we're going to talk about ferrimagnetic tunnel junctions, where essentially you replace the ferromagnetic layer with a ferrimagnetic layer. And really brief review back to what ferrimagnetism is. It's essentially anti-ferromagnetism, except each sublattice contributes differently, so you get a net magnetism. And the dynamics of ferrimagnetic tunnel junctions can actually be modeled using a standard LLG, but then if you assume that there's perfect anti-ferromagnetic coupling between the two sublattices, you can calculate effective parameters for damping parameters, gyromagnetic ratio, anisotropy, and then you can actually just calculate a single, modified LLG. And here I'm showing a macrospin model that I helped develop. And here, using the macrospin model, we can actually predict ultra-fast switching in the picosecond regime, which is 2 orders of magnitude faster than ferromagnetic switching. And as you can see, here's like a fun animation I made. So how do I go back? This ultra-fast switching regime comes at some caveats because we made some big assumptions. First, we assume a macrospin model where we're only simulating one spin for the entire device. That basically eliminates all possibilities of domain nucleation, multiple domains. How does that affect spin relaxation? And also, we're assuming, because it's macrospin, that thermal fluctuations are uniform, and of course, the perfect anti-ferromagnetic coupling. So for this class, this project, I wanted to try to relax these assumptions and try to simulate this with a microspin model using Mumax Plus. The reason I didn't use Mumax 3 is because it doesn't natively support ferrimagnetism. You'd have to kind of engineer two different sublayers and make them all, both the sublayers for anti-ferrimatically coupled together. But with Mumax Plus, they actually support it natively, where they're able to simulate two LLGs in each cell, and they're anti-ferrimagnetically coupled, and you can actually determine the strength of that coupling. And here, as we can see, even in like this fast one, okay, let's watch it reset. You can still see like kind of a domain wall forming there. And I took this further by simulating a bunch of different sizes. And as you can see, as we increase the size, and this is kind of what we expect from class, that we see these domains forming. And crucially, whenever you have domains forming at these larger scales, you can notice that the device actually doesn't switch all the way. Or if it does, it takes a very long time to do so. And if we go to the next slide, I've calculated the relaxation time. And if you just very quickly going from 50 nanometers to 200 nanometers, the relaxation time, where here the first two are the sublattice 1, sublattice 2, and then the bottom is the total. Oh, I have a laser pointer, I can use that. But you can see that this relaxes to about, this relaxes at it says 550 picoseconds, where in 200 nanometers, it doesn't even relax within 5 nanoseconds. And this makes sense because the exchange length, as you increase the size, like past the exchange length, then you start getting these multiple domains, which from class makes sense. And this introduces an additional energy barrier, which slows down the relaxation. So, okay. In conclusion, this is the first, to my knowledge, micromagnetic validation of ferrimagnetic tunnel true random number generation, which incorporates, again, all the things that macrospin model can't handle, which is domains, sublattice resolved thermal fluctuations, and essentially domains and domain wall dynamics. And by bringing in both a macrospin model and a microspin model, we can validate the quality of the random numbers and generate billions of random numbers, but then rein back the and increase the accuracy of this model by fine-tuning it with microspin model. Yeah, and that's my presentation. Thank you.